All right, so finishing this up, we're talking about direct current here. And direct current, as I have up there already, direct current occurs with batteries. And anytime you plug in a device like a laptop that has that kind of power box, your laptop and several other devices, when they plug into the wall and you have your cord, which goes to a box, which then goes to your laptop, those are examples as well of your direct current because that box converts AC to DC. Okay, so those are examples of direct current. Now, AC then is your alternating current. Alternating current. And you don't really have a flow of electrons. It's kind of a unique scenario where the electrons kind of vibrate. Electrons move, we'll say left and right just for argument's sake, left and right, and pass energy through the wire. So they don't actually flow. So you don't actually have an electron flow when you have alternate current, and that's a whole different beast on its own. And we're going to leave that one in the grade 11 course. We don't talk about AC a whole lot other than we make some assumptions and use some formulas, but we definitely don't have to worry about describing it because it's a little bit unique in that sense. So that's your, it comes from your power lines. Power lines, and then you have in your house. Sockets, that's all AC current. All right. So voltage, let's talk about voltage for a second. Here's the definition. The potential difference between 2 points. So how much work is necessary to move 1 coulomb of charge from point A to point B? We're going to talk about that in a lot more detail. I just want to introduce it because you have worked with it before in the grade 9 or 10 science course. So your symbol for voltage, we use capital V. The units is joules per coulomb. Joules per coulomb. And at this point, which is also known as volts, which is a V as well. So, so your voltage, a volt, is equal to 1 joule per, now I'm going to speak French, 1 joule for each or per coulomb. Okay, I'm going to leave it at that point there. So let's talk about resistance. You can see some of you might remember back to your grade 9 or 10 science course where I'm heading with this, but resistance. That's the measure of a material's natural opposition to the flow of electrons. So we're talking about a conductor, and we can put a numeric value to its resistance. So with resistance, we always use capital R in our formulas or equations. The units for resistance are ohms. Okay, and a bit of a circular argument here in some respects, but 1 ohm is a volt per amp. Okay, it's one of the forms here. 1 ohm is equal to a volt for each amp, or how many volts for each amp. And we're going to leave it at that. All right, because where we're heading with this then, oops, maybe I'll put it in here since I have some space. So remember or recall, the reason I went through and did those 3, you did V equals IR. V equals IR. Okay, and that's the relationship between voltage, current, and resistance. Okay, so it's the relationship between voltage, current, and resistance. So you did this and you want to put a box around, we're going to use this formula quite a bit coming up. But you should have already been introduced to it and had to have used it. Possibly the science teacher might have done it as a triangle. You know how I feel about triangles for those that have had me as a teacher before, and it looked like this. And I absolutely despise the triangle because it doesn't make you a better student. But anyway, this is what it would have looked like. Please don't use the triangles because they're only going to mess you up in the future as you move through science courses. So use your algebra skills that you learned in grade 9. That's all you need to do any of the algebra in any of the science courses. So finally, I just want to talk about force at a distance, electric fields. So when we talk about, you talked about like charges repel. So let's go back to that for a second. Like charges repel. All right, so we know that is one of the properties of electricity or charge. So if we have a positive charged particle, it's similar to Earth where it exudes a gravitational force, okay? We call it electric force. So there will be field lines, and the closer you get to this particle, the greater the force. So what we have is the convention for a positive particle is that instead of gravity pointed or pulled toward the particle, positive charge pushes away. Okay, and as a recall, these are what we call field lines. All right. Negative charge then is the opposite of that. All right, so the negative charge, again, it will have field lines as such. And the difference is it'll have a force pulling toward it. Okay, it's just the convention that we've come up with. And it has its field lines as well. So each line represents a certain amount of attraction or repulsion. So as you get further and further away from the charge, it gets weaker and weaker as you move away. Now, if we get that repulsion, and I'm going to talk about like charges repel here. So if we end up with two positive charges in proximity to each other, because the arrows are pointing in opposite directions in terms of repulsion or attraction, those two lines right there, those field lines, that interaction between those field lines is what causes those charges to push away. So positive charges are automatically repelling, and so they're pushing away from each other. So it's like looking at Newton's third law earlier, where one's pushing on the other's pushing, so they therefore equal and opposite reaction forces. So I just want you to realize again, similar to what we did when I talked about gravity, is that there is forces out there where no contact's required. So gravity was an example, and electrical force is an example. Of force at a distance. All right, no contact is required. When you put multiple fields in interaction with each other, some odd stuff happens. So I've got an app that you can take a look at, and it shows you how those field lines interact when they come in contact. But I'm not too worried about this here. Drawing those field lines, I just want you to realize that they do exist. So there's no homework associated with this section. It's more or less a review, going through getting everyone on equal terms. So any questions with that or anything you want further explained or any what ifs, please ask them in class, and I'll give you a hand straightening it out.